Cool. So we are going to continue what we were talking about last time, which is continuing on chapter 1 of the course reader, so in classical physics of cavities. So let me do a very brief review of what we studied last class. So this is a review of lecture 1. So in lecture 1, essentially, we started looking at how we can understand the physics of lossless cavity. And we set up an eigenvalue problem for a simple cavity in frequency domain. So we had an eigenvalue problem in frequency domain, which we were able to solve for a simple PEC cavity, and we explicitly calculated the eigenmodes and eigenfrequencies of the PEC cavity. But more generally, we were looking at cavities which have perhaps PEC, PMC, or a more general impedance boundary condition surrounding a region in space. Surrounding a region in space. And if we have such a situation where we take a region in space and surround it by these perfectly reflecting boundary conditions, which can be of many types, as I wrote down here, then what you end up having are the solutions of your eigenvalue problem are discrete. So you have certain discrete frequencies, omega 1, omega 2, omega 3, and corresponding electric field modes, E1, E2, which we are going to label as E3 and so on. So we saw what these look like for a simple, box PEC cavities, but for more complicated cavities, you in general can't write down analytical solutions to these problems, but you can always numerically extract these modes using a bunch of numerical techniques. And irrespective of what the exact cavity looks like, what the boundaries or the permittivity distribution of the cavity looks like, these modes satisfy some properties that are pretty global, like the orthonormality property or the completeness property, right? So we looked at two global properties. Of the cavity modes. So one property was orthonormality, which was that if you were to integrate epsilon x, let's say En star of x dot Em of x d3x, then you're going to get a delta function, which means that this is 0 if you're looking at different modes. So two different modes are orthogonal, and we choose it to be 1 if you're looking at the same mode, right? And this orthonormality property, as we started looking at it in more detail, implies that the cavity modes are physically independent. Right, so if you're looking at a simple linear problem with just the cavity, you put some source and you excite electric field inside the cavity. Essentially what this property allows you to do is think of each cavity mode as oscillating independently of the other cavity mode. And the mathematical basis behind this physical property is the orthonormality of the cavity modes. The second property that we looked at, which I stated in a somewhat loose way, and we're going to keep it that way, is completeness, which essentially said that if you take any physical electric field that you can set up inside the cavity, right? So if you imagine taking a source, which can be very complicated, it can be an arbitrary source, and you put that inside the cavity, it sets up some electric field, then this electric field you can expand into a sum of these cavity modes with some coefficient, say, of n, right? So, so this expansion is always possible. So you could, in principle, when you're thinking about electric fields inside the cavity mode, you could just think about these projections or coefficients in expansion onto the cavity mode basis, right? And this provides a complete description of the physics of the cavity. So these were two very important properties that we looked at. So I explicitly showed these properties for a simple cavity. For a more complicated general cavity, we did not derive this, but that's in the course notes. So you can go and look at it. It follows a very similar mathematical procedure as for the simple cavity. So you can look at it in the course notes, and there's a complete derivation of these results there. And based on these properties, then we started looking at the time domain picture of these cavities, right? So the second part of the last lecture was devoted to looking at what happens to the PEC cavities in time domain. So if you take a cavity, right, and you put some source inside it, right, then, and I look at the time domain Maxwell's equations, which is del cross E is equal to minus mu naught del H by del T, and del cross H is epsilon naught epsilon X del E by del T plus J of X comma T, so time domain Maxwell's equations, then what can we say about the dynamics of the cavity modes, right? So let's review this a little bit, and then we'll start building on top of the results of the section. So the idea here, the basic idea was to use this completeness property, which allowed us to describe the electric field by its coefficients on these cavity modes, right? So you could say that my electric field E, which is a function of X and T, I can expand it as a superposition of these cavity modes, and these coefficients would then change with time, right? Because you're taking a function of space and time, you're expanding it onto functions of space, right? So at each time, the projection of this electric field, which depends on both X and T, is going to change with time, right? So these are therefore time dependent. And if you plug these back into Maxwell's equations, so you substitute this into Maxwell's equations, and we did this in last class, in time domain. And then we were able to derive a set of equations for these coefficients an, and surprisingly, or maybe not surprisingly, they turn out to be the equations of harmonic oscillators. So you got d2 by dt squared, an of t plus omega n square an of t is equal to Sn of t, where Sn of t is the source driving the nth harmonic oscillator, or the nth cavity mode, was mu naught c square integral d3x, right? So this is what we ended up with. This is where we stopped in the last class. And the essential physical insight that came out of this mathematical exercise was that when you're thinking about cavity modes, you're essentially thinking about a collection of harmonic oscillators oscillating at the resonant frequencies of the cavity mode, right? And this is, even in time domain, the same picture holds. Although the cavity modes were computed in a frequency domain problem, we looked at Maxwell's equations in frequency domain and applied boundary conditions at the boundaries of the cavity, and then we came up with these quantized modes and frequencies. Even in time domain, a very similar picture holds, where each of these modes becomes a harmonic oscillator oscillating at the eigenfrequency that you obtain from the frequency domain problem. And if you're looking at the drive that is applied on the nth harmonic oscillator, it is equal to the overlap, a spatial overlap of the nth cavity mode with the source, right? So you essentially integrate the source that you have, which can be a function of space, with respect to the cavity mode that you're looking at, right? So this overlap integral tells you how much every source, how much a source is driving each and every cavity mode, right? So this is a very important feature, and we are going to exploit this when we come to the quantum part of the class, where we are going to be quantizing cavity modes, and then you'll see even in the quantum regime, a similar property will appear that you can express the physics of electromagnetic cavity by physics of n harmonic oscillators, and we see that happening already in the classical regime. So before we go on to make more conclusions, draw more conclusions out of the system of equations, one one thing that I might point out for completeness is that this is a second order differential equation, right? So we have a harmonic oscillator equation. It's a very, very simple second order differential equation, perhaps one of the simplest second order differential equation, but it is a second order differential equation. And to solve any second order differential equation, as you might have seen in a mathematics class, you need initial conditions. So you need to know what the coefficients an are at t equal to 0, and you also need to know what the derivatives of these coefficients are at t equal to 0, right? So you need initial conditions to solve this problem, which would be an of 0 and the derivative of an of 0, right? So once you have these, then you can definitely solve the system of equations for an of t. So how do we extract these initial conditions? Well, in a electromagnetics problem, the initial condition is given in terms of the electric and magnetic field. So in a typical electromagnetics problem, EM problem, so where you're solving Maxwell's equations, right? So where you're solving Maxwell's equations, the initial conditions are specified as the electric field as a function of space and at t equal to 0, and the magnetic field as a function of space and t equal to 0. And from these initial conditions, you can easily derive the initial conditions for the cavity mode amplitudes, right? Because if you know the electric field at x equal to 0, then you know that electric field at x equal to 0 is simply sum of the coefficients at t equal to 0. Sorry, electric field as a function of x at t equal to 0 is sum of coefficients at t equal to 0 times the electric field mode at x, so which immediately gives you from the orthonormality that this holds. E of x comma 0. Sorry, let me write this more clearly. Right? So this is one initial condition that you get. And of course, you have another initial condition, which is on the derivative, which you can get from the second Maxwell's equations. So which essentially tells you that the derivative of the electric field is del cross H, 1 by epsilon naught times epsilon x, del cross H of x comma t minus j of x comma t, and consequently, del by del t at t equal to 0 is simply 1 by epsilon naught epsilon x del cross h of x at t equal to 0 minus j of x at 0, right? So if you know the magnetic field at at t equal to 0, you can compute the derivative of the electric field at t equal to 0. If you know the derivative of electric field at t equal to 0, you can again use the expansion for the electric field and write this as sum over an, the derivative of an times en of x. And from here, you can immediately conclude that an dot of 0 is an integral omega epsilon of x en star of x dot del e by del t evaluated at t equal to 0, right? Which is nothing but 1 by epsilon naught x equal to 0 d3x, right? So given the electric and magnetic field at t equal to 0, which are the initial conditions that you would have for solving time domain Maxwell's equations, you can extract initial conditions for these harmonic oscillators, right? So that's one subtle point about this picture. So with these initial conditions, the dynamics of these harmonic oscillators are exactly formally equivalent to the dynamics of Maxwell's equations, right? So you can just solve one instead of the other. Right. So let's start looking at some implications of the fact that you have a bunch of harmonic oscillators that are describing the dynamics of the cavity. So what I want to go into is one specific problem where you think about the following. So you take your cavity, right, your lossless cavity. And this is a very important problem because this is going to connect lossless cavity to lossy cavities as well. So you take your lossless cavity and you put a source inside it, which is harmonic. So you put a harmonic source inside the cavity. So what do we mean by a harmonic source? Well, by harmonic source, we mean that the time dependence of the source is cosine of omega t, right? So let's take an example. So as an example, consider a source jx comma t, which is some function of space times cosine of omega t, right? So you have a harmonic source that is being driven at a frequency omega, and you want to see what this source does to your cavity, the electric field inside your cavity. Well, the analysis is quite straightforward. So let's see what happens. So because this Sn of t depends on the derivative of j, it also turns out to be harmonic. So the source Sn of t being applied to each cavity mode essentially also becomes harmonic. So Sn of t becomes some amplitude Sn times sine of omega t, right? So the sine comes because of this derivative. So there is a phase offset between the source in the harmonic oscillator equation and the source in your current source. And then the dynamics of your problem are essentially being described by a driven harmonic oscillator, right? Which is not very surprising. You're driving a cavity with a harmonic source, and because our cavity can be expressed as a collection of harmonic oscillator, you're essentially driving each of those harmonic oscillator with a harmonic source. So you have something like Sn sine of omega t, right? So this is a simple ordinary differential equation that I'm sure you all have seen how to solve in some basic mathematics classes on differential equations. So I'm not going to derive the solution of this differential equation, rather just tell you what it is and look at some implications. The derivation is there in the course notes, so you can go and read it if you're interested. So if you attempt to solve this differential equation and calculate an as a function of t, what you end up getting is something like this. So you get an of 0 times cosine omega nt plus an dot of 0 divided by omega n times sine of omega nt plus Sn divided by omega n square minus omega square sine omega t minus omega divided by omega n sine of omega nt. So it looks a bit complicated, but it is actually very simple to physically interpret, right? So if you look at the solution that we have for the harmonic oscillator equation under a drive, what you immediately see are that there are two frequencies that appear in the solution for an of t. So an of t has two frequencies. So one is omega n, which is essentially the natural oscillation frequency of the harmonic oscillator, right? So it's a natural oscillation frequency of the harmonic oscillator. And this frequency appears because this is it's an eigenfrequency of your electromagnetic cavity. So if you're trying to put some energy inside the electromagnetic cavity, you physically expect that energy to oscillate at the eigenfrequency of the electromagnetic cavity. The other frequency that appears in your solution is the driving frequency of your source. Of the source, right? So if the driving frequency is different from the frequency of the electromagnetic cavity, please note that the source is something that we are putting in, right? So we take a source and we put it inside the cavity. We are not really, this frequency omega is completely in our control. It's not determined by our cavity design at all. So you can design a cavity that will govern what your omega n's are, but the source can be at any frequency. It can be off resonance or it can be on resonance, right? So if it happens to be off resonance, which is when this is valid, so this of course is only valid for omega not equal to omega n, because otherwise you are dividing by 0, so that's invalid. So this is for off resonance. And when you're at off resonance, your solution has both the resonant, has oscillating terms at the frequency of the cavity mode, and it has oscillating terms at the driving frequency, okay? And what you immediately notice from here is that the electric field, which is governed by these coefficients a n of t, isn't 0 if you drive off resonance, right? So one important conclusion that is often misinterpreted in a lot of literature and a lot of discussions is that people feel that when you take a cavity and you drive it off resonance, you don't excite any field inside the cavity. That is not true. So oftentimes when we are looking at lossy cavities, that you don't really have a very precise resonant frequency, and you have a spread of frequencies that excite the cavity, right? Because you'll have some broadening, and we'll discuss that in a minute. So when you have a lossy cavity, then often one can make the argument that even if you're off resonance, you can have some electric fields inside the cavity because the cavity itself has some broadening in it. But even in the absence of losses, if you look at a perfectly lossless cavity, which has well-defined discrete set of frequencies that it should oscillate at, if you drive it at a frequency that is different from one of these oscillating frequencies, you will end up setting up electric fields inside the cavity, okay? And that is not new. This is the same physics as that of a driven harmonic oscillator. You will, if you drive a harmonic oscillator without any losses at a frequency that is different from the resonant frequency, the harmonic oscillator is still going to oscillate, right? It's not going to sit where it is. So this is not a surprising result, right? So the electric field inside the cavity exists even when the cavity is driven off resonance. Right. So now you might be somewhat surprised in the sense that, well, if an electric field exists, even when we are driving off resonance, is there any meaning to this resonance at all? So one thing that you immediately notice from these a n of t is that as you take your drive closer and closer to omega n, right, because of you have this omega squared minus omega n squared in the denominator, you would expect your a n of t's to become larger and larger. So a n of t becomes larger and larger. And we'll come back to this point in a minute, right? So the fields set up by a harmonic source become larger as the cavity is driven closer to resonance, right? Which is again something that you would intuitively expect. Now, there is a very interesting property of these lossless cavity, which is, now let's look at, instead of looking at the electric field, let's look at a metric related to energy, right? So let's look at how much power my source delivers to the cavity on an average, right? So let's see. So how do we calculate the power that the source delivers? So the power, yes, there's a question.
So right now in the lossless cavity, is all the omega are delta function?
Say that again?
So in the situation of lossless cavity, will the omega n will be a delta function?
No, omega n's are numbers, so they are the resonant frequencies of the cavities, right?
So is there any distribution of the natural spread of the omega?
So omega n, so for example, if you go back to the example of two mirrors, right? Then omega n's are two, n by L by C. So the frequencies that you would get if you impose boundary conditions on the two ends, right? So they are a set of numbers.
But that number, is there any fluctuation of that number?
No, that's constant. So if that is completely determined by your cavity design. So you fix your cavity, you get a set of numbers, which tell you what the resonant frequencies are.
But I think in this real situation, loss frequency should have omega plus and minus delta omega.
Right, but there's no loss here, right? We'll come to the PEC case in a minute. So right now we are looking at lossless cavity. So we take a PEC boundary condition, we put a source inside it. So your cavity modes are perfectly well defined, and that's why you're working with a lossless harmonic oscillator.
Sure. Okay.
Right. You're right. So if you add a loss, then and this is something you'll do in the homework, then you end up adding a decay term to this harmonic oscillator. Right. Mm-hmm. And then this decay term is what one way of interpreting that is a spread in the cavity frequency, or rather it would be a spread. It would give you an imaginary frequency, right? And that would have implications on many of its properties. And we look at that in today's class itself in a minute.
And also, do you consider any degenerate case of, for
so
example,
this completely captures all degenerate cases, because even if your cavity frequencies are the same, and if you have degenerate modes, the modes are still orthogonal, right? So even if your cavity frequencies are the same and you have multiple degenerate modes, all that you have to do is you'll have different harmonic oscillator equations for every degenerate mode oscillating at the same frequency, but they're still going to be independent harmonic oscillator.
Okay.
Does that make sense? So there are two, if you, let's say you have a degeneracy of 2 in your cavity frequency, right? So that means that there are 2 eigenmodes that have the same frequency, but those eigenmodes are still orthogonal to each other, right? Which means that the harmonic oscillators associated with those 2 eigenmodes are also completely independent. There is an arbitrariness to choosing those 2 eigenmodes. You can choose the 2 degenerate modes in many different ways, but that will not affect the result of your calculation. So any kind of quantity like power or electric field that you'll calculate will all come out to be exactly the same.
Oh, sure. Okay.
Does that make sense?
Yeah.
Okay, excellent. Right, so as we were saying, so let's now look at how much power does the source give to the cavity mode, right? So the power, this is electromagnetic theory, is given by an integral of J x comma t dot the electric field at x comma t, d3x, right? And you're going to integrate over all space, so which for us is the volume of the cavity. And if you use the expansion for the electric field, then you can write this as a sum over an of t, an integral j x comma t dot en of x d3x. And this then just becomes an overlap of the source with the cavity mode. Right. And this is, of course, just proportional to the Sn of t's that we had in our harmonic oscillator equation, right? So this just becomes the source driving the individual harmonic oscillators, right? So there is of course a normalization that we need to take care of, and all of that is in the lecture notes. I'll just write it out. So this just becomes sum over an of t times Sn star, so there's a conjugate happening, divided by mu naught omega c squared, right? So there is a normalization that appears. You can trace back a derivation of the harmonic oscillator to get this normalization precisely right, and it's also in the notes. But essentially, this integral is proportional to the source driving the nth harmonic oscillator, right? So the power. And this is the instantaneous power. So remember, this power is a function of time. I am only integrating it with respect to space. So this is an instantaneous power. So it is telling you at every time how much power my source is going to give to the electric field at that instant of time. And of course, it's almost always more interesting to look at the average power that the source delivers to the cavity over a long time. So we want to be able to calculate this average power, P average. And that is just, we'll just write it notationally as mu naught omega c square, do an average of an of t times Sn star of t. Okay, so now if you calculate this average, this is actually quite easy to do. So if you calculate this average times Sn star of t, So you know what an of t looks like, which is essentially this. And you know what Sn of t looks like, which is here, right? So you can put these two together, and what you will find. Sorry, I made a slight mistake. So this should be Sn star times cosine of omega t. Okay. Sorry about that, because there is a derivative, so that phase shift is important. So this is just Sn star times average of A t cosine of omega t, right? AT of cosine of omega t. So let me copy paste this equation for AT here so that you can see what's happening. Right? So from this equation, what you immediately see is that if I average A and t with cosine of omega t, if my omega is not equal to omega n, then all of these terms are going to vanish, right? Because they are going to be oscillating at different frequency. And if you average a product of two harmonics at different frequency, then they vanish. And the only harmonic that exists at frequency omega is the sine omega t term, and because it's a pi by 2 phase with the cosine omega t, it vanishes, right? So this is an important conclusion. So what this is telling us is that if you look at the average power that a harmonic source provides to a cavity when it is off resonance, this is 0 if you're driving off resonance. Okay, so this is one of the most important conclusions. So the average power being provided to the cavity of resonance is 0, right? And like physically, this makes perfect sense, right? Because what we see from our solutions to the electric field is that, well, the electric fields, if you're driving off resonance, they are not infinite. They have some finite value as given by these coefficients. Because the electric fields are not going to be infinitely large, it means that the amount of energy inside the cavity is always going to be bounded, right? So because the amount of energy is bounded, the source cannot possibly be delivering average power to the cavity, right? It's a lossless cavity. So if the source was in fact delivering average power to the cavity, then it would mean that the amount of energy inside the cavity would go on increasing with time indefinitely, and your electric fields would not be bounded, right? So because your electric fields are bounded, this is something that you would expect since your cavity is lossless. Of course, the moment you change loss, this picture will change, because then the source will have to deliver power in order to account for the loss mechanisms, right? So it would have to deliver power that is then being dissipated by the loss channels. But if you ignore any losses, then it doesn't deliver any power if it is off resonance, right? So this is one important conclusion. So this kind of gives us some notion of resonance. So if you're not on the resonant frequency, then you don't deliver any power to the cavity, right? So what about being on resonance? On resonance, right? So if we consider solving the same problem, so we solve our same problem, d2n by dt square plus omega n square an is equal to Sn sine of omega n of t. Now, instead of having sine of omega t, I'm driving it on resonance. Then what you can show is that your an of t, this is again, the derivation is there in the book, and this an of t, you could actually, the simple way of calculating this is to have a frequency omega here, and you take the limit of omega going to omega n, right? So you can essentially take the expression that we have here and take the limit of omega going to omega n. So it's a very simple mathematical exercise to show that this essentially just becomes an of 0 cosine omega nt, an dot of 0 divided by omega n sine of omega nt. But now you have a term t times cosine of omega nt, right? So now what you have here is that when you're driving on resonance, your field amplitude is increasing indefinitely with time, right? So this is t times cosine of omega nt, right? So if we were to draw a simple picture here, let's say for an of t, so off resonance, you would have, a bunch of resonant frequencies that are affecting your an of t. So this is it's going to oscillate back and forth. So this is oscillating at omega and omega n, right? But when you're on resonance, so this is off resonance. But when you're on resonance, then this goes on increasing with time. So there are some oscillations, but you have an increase. I guess it would more precisely look something like this. So there are oscillations that are happening at the resonant frequency, of course, but the amplitude of the oscillation is going to be increasing with time. So as your t goes to infinity, if you think about steady state, well, a steady state doesn't really exist because your cavity modes are becoming larger and larger, your cavity amplitude is becoming larger and larger, right? And in this case, if you look at the amount of power that is being transmitted, it actually goes to infinity if omega is equal to omega n. So the moment you drive your cavity at the resonant frequency, because the fields are becoming larger and larger, your source is actually supplying a lot of power to your cavity mode in order to make the fields larger and larger, right? So if we were to, let's say, make a plot, well, this is not an actual plot, but just a pictorial depiction of what this looks like, what you'll find is at the resonant frequencies of the cavity, you have these infinitely high powers being transmitted into the cavity and no power being transmitted off resonance, right? Now, as we'll see in the presence of loss, well, this is your homework problem. In the presence of loss, if you introduce some loss in your cavity, it can be radiation loss, but what is somewhat easier to handle theoretically is an absorption loss. If you assume the material inside your cavity is lossy, then you'll see that instead of being infinitely large, these becomes Lorentzians that are broadened by an amount that is determined by the loss. And this is kind of going to what Yisho was saying, right? So this broadening is governed by the amount of loss, right? And the power now doesn't hit infinity anymore, right? But it has some finite value, which becomes larger and larger as you make your system more and more lossless, right? So this then is what you typically would think about in the spectrum of a cavity. Well, if you do an actual experiment, then you have then you'll have some line width of your resonances and some peak value of the resonances. And those line width and the peak value being finite is just a consequence of your system being lossless, being lossy, right? Okay. Okay, so
maybe just a brief, comment. Yalin is here. On the relation between the frequencies of the lossy and lossless system, although I think people may look into that in the homework, because you indicated here that omega 1, omega 2 are the same as in a lossless system.
They do shift.
Broadening, yeah.
That is in the homework, yeah. So these frequencies will change a little bit based on the loss, and so there is a detuning that is introduced in the presence of losses. So if you look at the harmonic oscillator equation, you add this gamma n dAn by dt term, and you look at what the eigenfrequencies of the resulting lossy harmonic oscillators are, then you'll find that it is going to be slightly different from the resonant frequency. In the regime of low loss, they are very close, but yeah, there is a detuning as well. So yeah, so you'll be solving for an of t exactly in the homeworks and studying what this looks like. Okay.
Thank you.
Are there any questions?
If in the loss system, then we have infinite amount of omega.
In the lossless system.
In the lossy system, then are we going to solve the eigenvalue equation on the infinite amount of the matrix?
In practice, what happens is that you're typically only looking at frequencies that are close to the frequencies that your source is going to be exciting, right? So in practice, you're never really exciting with arbitrarily high or arbitrarily low frequencies. There is a frequency window that's of interest, and then you can focus your analysis on calculating frequencies within that frequency window, right? Okay. Also in practice, if you look at practical losses like coming from absorption or radiation, then those losses also select some resonant modes to be very, very lossy. So even though in a lossless system, you will have infinitely many resonant modes, there are most of those resonance modes that would exist in a lossless system would become incredibly lossy in the presence of any practical losses. So you wouldn't actually see a resonance there. in practice. And so there will be, so essentially then, what is it, a cavity or not? So it's more of a question of, if you find a high Q, a very narrow line with resonance, then you can think of it as a cavity. But if you look at these artificial problem where you put a PEC boundary condition, then of course you might have resonances that are, that would exist in a PEC problem, but they're artificial. The moment you remove the PEC boundary condition and come back to the real world, those resonances are going to disappear because they're just going to be incredibly fast. Okay, I think, does that answer your question?
Yeah, I can just add a comment to that. I mean, Raul already addressed it, but as you see from the problems that we'll be studying later, like lasers or cavity quantum electrodynamic systems, I mean, as Raul already said, there is a frequency region about which you care. That's where your atom or your active medium is. And, you make your cavity also of some material that has some absorption properties or refractive index properties that are dependent on the frequencies. So if you look at the resonator, it would be very ultra high Q at the frequency of your atom, but then you move to other frequencies, and there it's very lossy. And next week, when we talk about photonic crystals, there is also a finite frequency region determined by your structure even, which tells you that you can build high Q resonators only in a very limited frequency range, which is even smaller than the transparency region of your material, right? So you are right, there are infinitely many solutions to the eigenvalue problem, but generally you don't care more than about one or few of them for practical purposes.
So I can make one last point on this power, because I think this is very important and it's going to tie back to the density of states that we'll discuss at the end of today's lecture. So one last point to make about the power is in the lossless case. So in the lossless case, although we have written it as this power going to infinity on resonance and 0 of resonance, right? This infinity is of a very particular kind, and it's actually a delta function, right? So this P of omega, and this is again something that you're going to study in the problem set, is going to be a sum of this. Omega minus omega n, right? So you essentially, the power looks like a bunch of delta functions sitting at the resonant frequencies. And when you introduce loss, these delta functions broaden into, Lorentzians in the limit of low loss. So we are going to use this later on to make a connection between density of states for lossy and lossless systems. So in the presence of loss, these delta functions are broadened. Okay, so I think now we can take a break for 5 minutes and come back to this. Yeah, if you have any questions, we can discuss as well if you guys are online. Yeah, I also wanted to say that we'll start office hours from next week on Zoom, Wednesdays, 4 to 6.
Are you going to release the solution on the lecture notes? So
For the
yeah,
other exercises, yeah. The problem set solutions will of course release after the problem set is due. I also of course set up some exercises that are not on problem sets. I don't have solutions to all of them, but I would be happy to discuss them in office hours. I'll release the ones that I have solutions for, but not for all of them. But I'll be
or
happy.
maybe part of them is already pretty helpful.
Okay, yeah, I'll collect some solutions and maybe post it.
Thanks.
And I'd like to add comments on my office hours, since I was not here on Tuesday. I mean, of course, Raul will handle questions regarding homework in his office hours. If you have any questions for me, since we have a virtual quarter, and I will be primarily addressing questions regarding the course material and lectures that I'm teaching, then you can just send me an email and we'll arrange to meet over Zoom. I didn't want to keep specific slot during the week, so that probably most questions that you will have will be one-on-one, and we can actually address them at whatever time works for you and for me. Okay, so we will not announce specific time, just send me an email if you have questions, and then we can arrange my office hours.
Okay, can we start, or people need more time?
Virtually, everyone is here still, so I think we can start. The number of people, participants hasn't changed, so I don't know what that means. Yeah, I think you can keep going since we're recording.
So I'm just coming to the last part of chapter 1, and we'll probably be able to finish it next 10 to 15 minutes. And that is on lossy cavities. Right, so we spoke quite at length about lossless cavities. So of course, as I prefaced our discussion on lossless cavities in the last class, it was with the fact that these are a nice model that allow us to study the essential physics of cavity systems and the essential physics of light confinement. But for practical calculation, they're mostly not as useful because in practice, you always have losses of many different kinds, right? So in practice, in optics, there are two types of losses that are very common. So one loss is called a radiation loss, right? And this radiation loss essentially exists even if your dielectric is completely absorptionless, right? So even if your dielectric has no imaginary path, the dielectric constant is perfectly real. So you would expect the dielectric by itself to not absorb any power, but it is hard, it is impossible almost to make mirrors that are perfect, right? So even with lossless dielectrics, you can't make mirrors that that reflect at unity reflectivity. And those imperfections are very fundamental. And Jan and I will be talking about how you can go ahead and design these perfect mirrors in the next few lectures, or near perfect mirrors in the next few lectures. And you'll see that if you try and design a mirror in a finite region of space, it's almost fundamental that you're going to have a finite, less than unity reflectivity, right? And due to this less than unity reflectivity, you essentially will have losses in your cavity. The other loss that arises in these systems is absorption loss, right? And these absorption losses are due to, as the name suggests, material absorption, right? So your dielectric by itself, based on what material you're using for your cavity, and of course, a lot of this course is going to be focused on more practical aspects of these losses and how they look like in different cavity architectures. But these absorption losses are coming from the material absorbing photons, dissipating them into other mechanisms. Like they might be, there might be Joule losses because your photons are being absorbed. They're generating electron-hole pair, which are then being lost. Or there might be, coupling to your photons being absorbed through a phonon process. So there are many, many different physical mechanisms that can result in your material taking energy from optics and transferring it to some other kind of energy. And those material losses again make your cavity lossless. So in your homeworks, you're going to be looking at a problem. In this homework, you're looking at a problem in which you have material loss, and then you're also looking at a bunch of problems in which you have radiation losses, because you're making mirrors that are near unity in reflectivity but not identical. So you'll get more idea of practically where these losses come from. But what I'll do over the next 15 to 20 minutes is give you some definitions of terms that we use in describing these lossy cavities, right? There are things that you might have heard before in other contexts, and we'll just review those terms and essentially describe general properties of lossy cavities. So right now in this chapter, we are not really interested in analyzing specific cavities for their losses, but what would generally happen if you have a lossy cavity, right? And if you are looking at a specific cavity, you can always tailor these definitions and techniques to those specific cavities. And we'll do that in this course as well. Right? So the first set of terms that we describe is, one of the most important term with respect to lossy cavity is quality factor. And associated with quality factor is this notion of a photon lifetime, right? So to start thinking about what happens when you have losses, well, as you would expect, in frequency domain, as I alluded to, you have these narrow delta functions are broadening into Lorentzians. It is maybe easier to think about that in time domain, right? So let's do a very simple thought experiment. So we have a cavity which is almost lossless, right? But maybe it has, slight material absorption loss, right? So maybe it has some material absorption loss. Right, or it can also have radiation loss, but for the purposes of this experiment, let's just think about material absorption loss, right? So now, if this cavity did not have any losses, then we know that the coefficients a n of t of the cavity mode would just oscillate as cosine of omega n t, right? So they are just going to be oscillating at the resonant frequency of the cavity, right? Now, because you have losses, so now if these losses are, let's say, very, very small, so they don't really they don't really affect the cavity in one oscillation, but they affect it over several oscillations. One simple thing that you could think about is what happens to the energy of the cavity after one period of oscillation, let's say, right? So we have a period of oscillation t associated with the frequency. So what happens to the energy of the cavity? Well, clearly the energy decreases compared to its value before a period, right? Because there is some losses. And this decrease is proportional, in fact, to the amount of energy that you started off with, right? Because the losses in the cavity, be it radiation losses or material absorption losses, they are proportional to the square of the field amplitude inside the cavity, right? So material absorption losses depend on sigma E square, where sigma is your conductivity. If you have radiation losses, it depends on how much power is escaping the cavity, which again is proportional to the square of the field inside the cavity, right? And the square of the field inside the cavity is proportional. If you're just looking at a single mode cavity where everything is just described by a single coefficient a n of t, is going to be proportional to the amount of energy inside the cavity. So you could say that this is in fact proportional to u of t, right? And if your time period is small enough, if your frequencies are very large, which is typically the case in optical cavities, this just becomes proportional to the derivative of u of t with respect to time, right? So what we get from this very, very simple notion that the losses are being absorbed as per a law that goes as square of the electric field is that the derivative of the energy with respect to time should be proportional to the amount of energy, right? So in fact, we can introduce, let's say a constant of proportionality kappa and write down a very simple equation for how we expect the amount of energy to change. Right? And this should definitely hold when your losses are very, very small. Of course, if you have very high losses, then this simple model doesn't really hold, because your because of the losses, the energy inside the cavity is going to change significantly within one optical cycle, and then simple exponential law doesn't really hold. But if you're looking at cavities that are oscillating much faster than the time scale on which loss is happening, then you can definitely expect that the derivative of the energy inside the cavity is just proportional to the amount of energy inside the cavity. And this immediately tells you that the energy inside the cavity, then you would expect it to just decay exponentially with time, right? So here, then we can define the notion of a photon lifetime. So the photon lifetime is essentially the amount is related to this proportionality constant kappa. So kappa governs how much loss I have in my system. If my kappa is very large, then that means the derivative of my U is changing, is large. So so the amount of loss is large. And if your kappa is very large, then you can see that this exponential decay happens much faster, right? So you can introduce a photon lifetime, which essentially tells you what is the time for which the photon stays inside the cavity, right? So before it is either absorbed in the material or it leaks out of the cavity, based on whether you have a material absorption loss or you have a radiation loss. And this photon lifetime is essentially defined as the reciprocal of this kappa. Okay, so one important point to note is that if your energy decays as exponential minus kappa of t, the electric field is going to decay as exponential minus kappa t by 2, right? Because the energy is proportional to the square of the electric field. The photon lifetime is defined as per the decay of the energy, not the electric field. So that's one important point to keep in mind. So the other...
Can I just say, sorry for interruptions, that in Roll's notation, kappa is the energy decay rate, and kappa half would be field decay rate. In the papers, and some of the papers that we'll also be reading, people use different notation. And in atomic cavity theory, often they use kappa as the field decay rate, which would be half of what Roll has defined here. It's a matter, I mean, it doesn't change anything, but just make it clear how you're defining your decay rate, and make sure that you understand how others are defining this decay rate. Don't get confused if you see a factor of 2 difference when you're reading papers. Yeah.
Right. So, so the other important metric that we often define with respect to these cavities is this quality factor, right? And this quality factor essentially, sorry, before we go on to quality factor, let me make another point about these decay rates. So that is additivity of the decay rates, right? So, and we'll see this very explicitly when we talk about couple more theory and build models of how cavities and different loss channels are interacting. But in many physical problems, you often have, multiple channels through which you're losing energy, right? So even with my very simple description of losses, you could have radiation losses and absorption losses, right? And often you can characterize how fast you will have radiation losses and how fast you'll have absorption losses, right? So one of the things that I might point out, in practice, it's often easy to simulate radiation losses, right? Because you essentially have to solve Maxwell's equations, figure out how imperfect your mirrors are based on electromagnetic simulations. It is somewhat more challenging to simulate material losses, because material losses are often not very well calibrated, right? So you can simulate radiation losses, and then in experiment, you go and see a Q factor or a decay rate that you have experimentally measured. And so then you can imagine partitioning that decay rate into decay rate coming due to radiation losses, absorption losses, or any other decay mechanisms. And one of the important properties of this decay rate is that it just simply adds up with respect to all of these loss channels, right? So the way to think about this is that, let's say you have your cavity and you have, a bunch of loss channels. So you have channel 1, which is radiation losses. You have channel 2, which is absorption losses, right? Or you might also, of course, want to, you might divide these channels into finer channels based on your cavity design. So your radiation losses can be maybe due to in-plane confinement, out-of-plane confinement, and so on. And we'll look at this when we go to precise cavity designs. But in general, you can divide up your loss mechanisms into multiple channels, right? And then if you're looking at the derivative of the amount of energy, then each of these loss channels essentially gives you a power that is proportional to the energy U, but proportional with different proportionality constants. So you can define these decay rates into different modes in general. So this would be decay into maybe into channel 1, channel 2, and so on. And so you can then collect all of this into one decay rate, and this decay rate is simply a sum of all of these individual decay rates. So your decay rates in any physical system are going to add up when you have multiple loss channels, right? So this is obviously a very, very simple idea. If you have multiple loss channels, you add up decay rate, but it is important to realize that it's coming because of the fact that all of these decay channels are decaying at rates proportional to the square of the field amplitude inside the cavity, and that's only when you can add up all of these losses, right? If, let's say tomorrow, it's not going to happen, but let's say if someone comes up with a decay mechanism that doesn't go as proportional to square of the electric field, but proportional maybe to the 4th power of the electric field or something like that, then you will not be able to simply add up this decay rate, and you'll have to handle these separately, okay? So that's one important point, okay? So as I was saying, the next important term that we often define is quality factor. And this quality factor, Q, you can actually think of as 2 pi times number of optical cycles within 1 photon lifetime, right? So that's a very simple mnemonic to remember what this quality factor means, right? So you want to count how many optical cycles have occurred by the time you have elapsed 1 photon lifetime. And remember, the photon lifetime is 1 over the energy decay rate, right? So based on Yelena's comments, we would explicitly call this the energy decay rate, right? And this is quite simple. So this is just 2 pi times the photon lifetime divided by the oscillation, the time period of the cavity. So the time period of the cavity is just 2 pi over the frequency of the cavity, right? And TP is the photon lifetime, which we defined as 1 over kappa. So this quality factor is also just equal to omega c over kappa. Okay. So for a lossless cavity, kappa is 0, so your quality factor is infinite. For a lossy cavity, you'll have a Q factor. The larger the quality factor, the more lossless the cavity is. And because these kappas add, these quality factors add in reciprocal, right? So for multiple loss channels, your total quality factor is given by 1 over the sum of quality factors over the different loss channels, right? So if you're combining quality factors, if you have quality factors for different physical mechanisms that are introducing loss in the cavity, to add them together, you kind of need to reciprocate them and then not add them directly. Okay, so this is one simple definition. And a very important feature that we can almost immediately see is a relationship between this energy decay rate and the spectral features of the cavity, right? So relationship, and this is all very heuristic. So we are just looking at very general physical properties between energy decay and spectral features. So as we saw that the electric field A of t essentially varies as cosine of omega c of t in the absence of loss. And if you add loss, then you'll have this exponential minus kappa t by 2. So in practice, this omega c also shifts around a bit, but let's call omega c as the renormalized cavity frequency, right? So you have an exponential decay coming because of loss, and this coming because of the natural oscillation of the cavity. Then if you look at, let's say, the spectrum of the cavity, so how does the electric field look like in frequency domain, then you're going to be doing an inverse Fourier transform on this A of t, right? So you're going to be doing an inverse Fourier transform on this A of t, and this gives you a Lorentzian that is centered at omega c and with line width of kappa. So I'm pretty sure all of you can do this on your own. So this Fourier transform essentially just gives you a Lorentzian that is centered at omega c, and it has a line width governed by kappa, right? So if you plot this Lorentzian out, right? So it's going to be centered by omega c. Let's say this is the maximum value of the Lorentzian. If you look at where this Lorentzian becomes half, then this line width is going to be exactly equal to the energy decay rate. So oftentimes your quality factor can be estimated based on the frequency domain, the spectral properties of your cavity, as omega c divided by what is called the 3 dB bandwidth of your spectrum, which is essentially the point at which your, this is 3 dB. I always have big confusion in remembering this. So essentially the point at which your amplitude of your spectrum becomes half of the resonance value, right? So this is extracting Q from resonance. Okay, so these are two very important terms about the losses in the cavity. And before we conclude this class, let me make a few comments on two other important terms with respect to lossy cavities, which actually one sees very frequently in solid state physics, in the counterpart of cavities in solid state physics. So it is important to understand what they are in the context of our, in the context of our optical systems. And that is related to the density of states. So lossy cavity. So you can read about this more in 1.3.2. Right. So now if you think about lossy cavities, especially cavities with radiation losses, so this is a chapter, especially cavities with radiation losses, then we no longer have solutions to Maxwell's equations that look like cavities, right? So in fact, what happens then is that the solutions of Maxwell's equations form a continuum. They are no longer discrete solutions anymore, but they form a whole continuum of solutions. So at every frequency, you can construct an eigen solution of the lossy cavity. So one way of thinking about how you would do that, so imagine you have a cavity, but this cavity is not formed with perfect electric conductors or magnetic conductors anymore, but with some permittivity distribution epsilon of x. So to construct an eigen solution at frequency omega, all that you really need to do is solve a problem in which you scatter a plane wave against this cavity and look at electric fields in all space. So the electric fields that the plane wave sets up in all space are going to satisfy Maxwell's equations, but subject to the radiation boundary conditions. And therefore, there are going to be solutions of this eigenvalue problem. But you can clearly see that you can construct the solution at any frequency omega. So the discrete nature of the frequencies doesn't really show up the moment you remove the losses in the cavity. And this is what we see. In the, like the broadening of the spectra of lossy cavities, that a very infinitely sharp spectra at the resonant frequency doesn't really exist anymore. So with respect to these,
the reason why we see infinite amount of omega is because the boundary condition doesn't
exactly
has a condition.
Yeah, so boundary condition then becomes a radiation boundary condition. It's not perfectly electric anymore, and that is that results in the frequencies not being discrete. So you don't. Yeah, so you don't have a condition saying set the electric field to 0 at these points, which is essentially what results in the standard.
Yeah. Does it have to be a radiation boundary condition, or would this also arise from the absorption condition?
That's an excellent question. So if you have PEC boundaries, but with material absorption, then you can still describe the electric field with discrete set of modes. Because you could ignore the absorption and solve the problem of the of a lossless problem with the boundary conditions, PEC boundary conditions, and then you will still get like an orthonormal set of modes that you can use to describe the dynamics of your cavity. The harmonic oscillator would just become a damped harmonic oscillator.
I see. Thanks.
Right? That's what would happen. But the moment you look at radiation boundary conditions, that's not as simple anymore. And then you cannot come up with a discrete spectrum of fields. And so then you necessarily have to go into a continuum. Okay. Great. Yeah. So you can construct this continuum. So this is specifically, this happens when you have radiation boundary condition. When you have absorption, there are some mathematical tricks that you can play, but in practice, you always have radiation boundary conditions, right? So then you can think about counting the number of states that you have per unit frequency, because you have a continuum, so you can define the density of states just as you do in solid state physics, right? And the density of state is irrespective of what structure you have. The density of state is just the density of state of free space, right? Because what I'm talking of, the way we are constructing our states is by shining plane wave. So there is a one-to-one correspondence between the electric field that the structure is setting up and the incident electric field. So for every plane wave, I can construct an electric field mode, right? So if I'm counting the number of electric field modes that I have for a complicated structure, I can simply count the number of ways in which I can excite the structure, right? And consequently, the density of state is just the density of state of free space, which you would have calculated countless number of times in quantum mechanics classes. So which I'm going to just write down here. So omega square NB cube upon 2C, where NB, this is the background index. Okay, so this is what the density of state looks like. So irrespective of how resonant your structure is, the density of state scales as omega squared, right? So this is what your density of state looks like. And let me contrast this with the density of states of a lossless cavity. Because a lossless cavity has a resonant frequency at specific eigenmodes, this density of states is just a bunch of delta functions, right? Because then you only have specific eigenmodes. So the density of state is essentially the derivative of these specific eigenmodes. So you just get delta functions. So you only have a state if you're looking at a narrow frequency window around the resonant frequency. You don't have a state otherwise. So this is what your density of state looks like, right? So and a related concept to these density of state is what is called the local density of states. And this is again defined in the chapter. So I would encourage you all to read it there. So this local density of states is a better metric for optical cavities, because in optical cavities, we are often interested in looking at how point dipoles are emitting into the electromagnetic structure. So like when we are going into studying quantum optics, we are going to have these point two-level systems emitting into electromagnetic structure. And then it's no longer as important to answer the question of how many states exist, but it is more important to answer the question of how many states exist at the location of the dipole, right? Because those are the states that are going to affect the dynamics of the dipole. And this local density of states can be rigorously defined is proportional to the power emitted by a dipole at a particular position, right? And if you look at the local density of state of a lossless cavity, sorry, I'm rushing through a bit because we are out of time, but if you look at the local density of state of a lossy cavity versus a lossless cavity. So for a lossless cavity, you'll again see these delta functions, and we've kind of calculated this because this is just the power emitted by a source. So when you hit the resonant frequency, you get delta functions. But when you look at these lossy cavities, then unlike the density of state, which just scales as the free space and therefore erases any information about the cavity, the local density of state gives you broadened Lorentzians. And one of your homeworks is simulating this local density of state for a lossy cavity. And you'll see that as you increase the Q factor of the cavity, this local density of state actually tends towards the local density of state of a lossless cavity. So whenever we are going to be talking about cavities in this class, and if you want to assign a notion of a density of states, then you have to look at local density of states and not density of states, unlike in solid state physics, where density of states is what is the most important metric. Okay, so I'm going to stop here. So I rushed a bit towards the last part of this class. I'm sorry about that, but you can look at chapter 1.32. This information is very qualitative anyway. There are no derivations here. So you can look at chapter 1.32 and perhaps read it on your own. And if you have any questions, I would be happy to answer in office hours.
Maybe I can say just I know we're over time, but just in the last minute, if you're done, Raul, just a comment. Yeah. Yes, on the Density of states, I mean, whenever you solved it in quantum mechanics or physics of semiconductors, you're basically counting number of modes per some unit frequency interval. That's what the density of states is. So Raoul made a comment that it scales with Q, and you basically see that because if you have a mode with a Q factor, particular Q factor, line width is proportional to omega, central frequency over Q. So if you look at kind of count number of modes per certain frequency interval, you have 1 divided by delta omega, and that scales with Q, right? So that kind of gives you intuition that the density of states scales with the Q factor. And we'll do more of that certainly later when we do cavity QED. And I also wanted to make one easy, maybe obvious comment regarding the Q factors, that Q factor is a property of a particular mode and not a property of a resonator, although you will often see a resonator and some value of the Q factor, which is generally for the highest Q factor mode of that resonator. So each mode, which is this orthonormal solution of the eigenvalue equation of the resonator, has a specific Q factor and also a mode volume that we'll be talking about later on. And finally, also what Raoul was talking about, photon storage time. Photon storage time doesn't mean much unless you know also the frequency of the resonator or the optical cycle of the resonator. So if you are quoting a photon storage time of a microsecond, that would correspond to the ultra high Q factor in optical frequencies. For a microwave resonator wouldn't be such a high Q factor. So that's why Q factor is basically defined as the number of optical cycles that you fit within the photon lifetime, right? Photon lifetime or photon storage time on its own doesn't really mean much unless you are also introducing the frequency or optical cycle. Okay, that's all I wanted to say. We're just over time also. We'll close it.
You next week.
I'll see you. We'll see you next week on Tuesday. Yes, and we'll start chapter 2, photonic crystals and actually mechanisms for confining light and reducing radiative loss by structuring resonator.
Yeah.
You have questions or someone wanted to say something? Or?
Yeah, the homework I would do in 2 weeks. So just, so I'll end the meeting now.
Yeah. Bye, everyone. Bye-bye.